everyone, how's it going? My name is Liz from the Dfinity Foundation, and welcome to Community Conversations. So this is an opportunity for you, the community, to hear from contributors in the internet computer ecosystem, as well as ask them questions live. So today we have our very own Roman Kashitsin, Senior Software Engineer at Dfinity Foundation, here to give a talk on best practices on canisters in Rust. So feel free to take it away, Roman.
Thanks, Liz. So my name is Roman. I have been working at Dfinity for more than 2 years and worked on various levels of the platform, including execution. Was like the first developer on the message routing team and the Eng lead afterwards. And I also contributed to the first implementation of async in Rust CDK. So I know pretty well everything which is going on when your canister is executing on the replica. So I find canister development very enjoyable and a refreshing experience. But because it's like new type of software, people have questions when they want to develop something, especially in Rust. We observed some patterns, like we developed quite a few canisters ourselves, including like ledger canister, internet identity, governance, and like plenty of other canisters. And some like questions and patterns appear over and over again. And I thought it might be helpful to compile common questions into like a talk, and just to save you some time when you develop your own things on top of internet computer. Just a disclaimer, it's not an introductory talk. I'm not going to explain how to use Rust or how to install the Rust CDK. I think there was already a talk by Hamish, right, when he walked through the whole development process. So you might want to watch this before rewatching this talk. And I mean, even though there is a Rust in the title, like 60-70% of the talk applies to all canisters, not just Rust canisters. So even if you write in Motoko, I hope you will find something useful here. Yeah. Okay, so I divided talk into 3 parts. First, like code organization, mostly how to organize code and what patterns to avoid. Then we'll talk about infrastructural stuff like upgrades and builds. And the last part will be like a short one dedicated to observability, like how to check what your canisters are doing. So let's start from the elephant in the room, global variables. I think like many who try to develop something in Rust hit like this first. So the way canisters are organized is they require you to have some global state, because you don't have like control over your canister execution. You only expose methods which are called automatically by the system when you receive messages. You need to have some place where you keep the data between the calls. And because calls are like global functions, the state has to be global as well. And like the first question, like, okay, how do I define a global variable in Rust? And there are more than one way of doing this, and Rust makes it explicitly quite painful to use global variables. So the best pattern we found so far is basically to use thread local macro provided by the standard library and ref cells from the std cell package, well, and cells as well, depending on what type of data you have. This is like the safest pattern you can imagine, and we will see alternatives and ways in which thread local help you later on. So first, let's see some other ways of doing global variables in Rust. So our own ICCDK package provides storage abstraction, which allows you to get a mutable reference indexed by type. So you pick a type you want to store, you pass it to a getMute function, and it returns like a mutable reference to this data type. It looks very convenient, but it's actually, I would not recommend to use it. I think adding this abstraction to the CDK was a bad idea. The reason it's broken is this function is unsafe, but it doesn't declare itself that it's unsafe. And the problem is it allows you to get multiple mutable references to the same data, which is what Rust is designed to prevent. So the whole Rust type system, it prevents you from getting two mutable references to the same location in memory. And we will see on like next slide why you want to keep this keep this guarantee in the language in Canisters. So another pattern that you can see in quite a few places, including, for example, governance Canister, the latest release, is you just use global variable like static mute state and just whatever state you want to have there, and then you initialize this state in your init function, for example. So again, in this case, Rust will force you to use unsafe, but what most people do, they just define functions which look safe, but do the same thing as getMut. I guess this was like the getMut function provided by the ICCDK was a reaction to this repeating pattern. So this is still a bad idea because, again, you have exactly the same problem. You might have multiple mutable references to the same data. So another example is actually safe, but I find it very confusing. So what you could do is you can use lazy static macro from the package called lazy static, and you can use like a read-write log from the standard library. This effectively gives you a global variable. And the main issue with that is that you're depending on where you compile to native code or into WASM or WebAssembly, semantic of your program will be different. For example, when I first saw it, I wasn't sure how it behaves. Like what happens exactly when I try to get two mutable references to the same object? Will I lock somehow? Because this is what happens in a native code, right? You will just lock. But in WebAssembly, you cannot block except for a call to another canister. So like what exactly happens? And so actually this behaves a lot like thread local variable. So if you try to get two mutable references to the same location, you will have a panic in your code, which I find this confusing. And depending on which target you compile to, you will have different behavior of your program, which I find like bad, very penalizing to mental tokens. So, and we'll see some other ways in which this pattern might be dangerous a bit later. So why exactly don't we want to have two mutable references to the same location? So let's imagine that we have simple function. You give it like a user ID and the friend, which just data. So you want to add a new friend, and the friend is not part of the state of your canister yet. I mean, it's a bit contrived, but I think it demonstrates the problem well. So what we can do first, we can go to storage. I use storage here, but if you use the static mute pattern, it's effectively the same. So we get like a mutable reference to our user. Then we add another user, like getting like another mutable reference to users, and add the new user. And this might actually break the reference that we already had. And here, I mean, it's the very next line, but you can imagine that this might be a function called from a function called from a function called from a library. So you don't even see it in your code. And the fact that you modified the data structure, it might, for example, it might have been a vector underneath. And when you added a new user to your user database, the vector might need to grow. So the system will drop the original memory. Well, before that, it will allocate new memory, move all the users to this new memory, and drop the old memory. And the reference that you obtained first, it will be not valid. It will be pointing to garbage. And then we can, for example, why we kept the reference in the first place, we wanted to add the friend ID to the list of friends. And this might corrupt your heap. For example, maybe this memory is already used by something else. Who knows? And you can't see anything wrong with this code if you just look at it. I mean, it looks perfectly nice. You have like safe Rust, but the behavior is very unsafe. And we don't even have any asynchrony here. This is like synchronous simple code. And if asynchrony enters the scene, it's even more complicated. Yeah, I would strongly recommend not to break language guarantees, because if your canister goes astray and we commit the state, it might be like there might be no way back. If you corrupt the state of the canister, you might lose your data. So the stakes are high. I would recommend not to use unsafe Rust if you are not very confident. So the next thing I would like to talk is like where do you place your global variables? So we know now how to declare them, like where to define them. So I think, in my opinion, the best approach is just to take your main file where like you define all the methods or a canister and just put all the global variables in one place. So that it's easy to see and understand where the state is. Because I saw quite a few times where people split the state across multiple files, for example, and then when you need to verify that what happens with your state, for example, you want to review the code and make sure that during upgrade, all the state is successfully transferred to the new version of the canister. And if your state is split across multiple files and like libraries, and then it might be very hard to be sure that all the state is like safely transferred. And if it's all in one file, you just look, okay, what do I need to transfer? What is actually transferred? And then you can have much more confidence in your program, in the correctness. And I mean, it's not a hypothetical problem. I think the very first issue that we have with system canisters is like somebody didn't check upgrade, and not all the stuff was transferred to the new state. So I would also recommend to explicitly state what should be saved across upgrades and what just temporary data, like some caches. I mean, I used terms borrowed from the Motoko language. They have a notion of stable variables and flexible variables. Stable is data which is persisted across upgrades, and flexible variables are not persisted. I mean, in our case, it's not like language construct, and you still need to explicitly transfer the state somehow. But at least it's nice to put intention into the code, like, did you intend this to be transferred or not? And I mean, if you are the sole owner of a canister, I mean, you can just keep it in your head. But if you have multiple people on the team, as we do, it's very helpful to know the intention. Yeah, so now we discussed global variables, and the next topic is very. I think many people have the issue, how do I debug and test my canisters? I think this is like the second question you have when you start developing. And to be honest, like debugging and testing infrastructure on an internet computer are probably like the biggest pain point at the moment. It's very hard to debug code running on an internet computer. Of course, we want to improve this, but it's not easy. And my experience is that testing and debugging is so much easier if you do it using the standard Rust toolchain. And the easiest way to achieve this is just write most of your code as if it's a library, and the library doesn't care much if it's used in a canister or not in the canister. And this way you could just write normal unit tests for your libraries, check that all the pieces work together nicely, and then you have your main file with the bulk, like with the minimal code required to assemble canister out of the libraries. You can still write tests against canisters. For example, the easiest approach is probably you can have some bash scripts starting a replica using DFX to call some methods on canisters. So you can still test the your canister code, but it's much more painful comparing to just using cargo test. And yeah, I would also say that organizing your canister this way makes it easier to understand, makes it easier to evolve, and makes it easier to find errors. Also, if it's a library, it doesn't contain global state as per previous recommendation. So you can just initialize state in native code and run all the tests. And because all the global state is in a canister, you just pass references into library functions, and everything works nicely. So I use this pattern in quite a few canisters, including Internet Identity. And I was very satisfied with that. Yeah, one last point is, even if you need to have access to some like internet computer specific functionality, for example, stable memory, what you could do is you could build like local abstraction, like abstract stable memory. Just say I have a trait which provides some methods, and you can have like fake but faithful implementation of this trait, which, for example, emulates stable memory as a vector. They have the same semantics, basically. Vector is like a poor man's stable memory. So you can abstract your complicated code, which needs to talk to stable memory, over like the trait, and then you can still test in native code using standard infrastructure if you write your own small stable memory implementation in native Rust. Okay, so now a topic which is a bit controversial, but I strongly believe that this is the way to go in future, is what to do with candid in Rust. So if you ever used Motoko, probably you enjoyed the feature when you just write your actor class and you define some method, make them public and like share it, and the compiler can generate interfaces for you. This is a very nice feature, especially if you just started developing and your interfaces change all the time. Just committing to something and maintaining 2 copies of interface and the implementation is painful. But I would say that in the long run, once your interface stabilizes more or less, like generating an interface from the implementation is just the wrong way to approach the problem, because to other developers on the internet computer, your candid file is the most important piece of information about your canister, basically. Like, what can your canister do? What do I need to pass into your methods? What do I get back? And what's the semantics of the methods? And all of this can be nicely described in your candid file. You can put comments in there. You can if you don't want to expose some functions or you consider them like internal functions, you can just avoid putting them in this handcrafted candid file, but still have them in implementation, for example. So your public face, the like public face of your canister should not be exactly the same as your implementation defines. So my recommendation would be that you write candid files by hand and like comment them carefully. Another recommendation is if you return some errors, make them explicit in the code. Like just define variants. Variants are very nice, and this corresponds very nicely to the standard way of doing error handling in Rust as well. How you do error handling, you use result type with like good result, okay result, and the error result. And the error result is enum. So variant in Candid is basically enum. Yeah, don't forget to put comments in there. The interface I put on the screen is kind of interface of the ledger canister, as it should be, and probably will soon be. So yeah, one question you might have is, okay, I have this handcrafted Candid file, which looks very nice, and I have my canister written in Rust. How do I make sure that my interface agrees with my implementation? And this is a very good question. So my answer to this is you can use Candid tooling, which is pretty good, but it needs some assembling right now. So the Rust SDK provides function like macros that you can put into your code, and the library will generate your Candid interface for you. It's a bit like Motoko, but you need like a bit of hand assembly to say, okay, this method is like a Candid method, and I want this to be the name, or this method is init method. So you need to put explicit annotations, and then you can get the interface of your canister as a string. Basically, it composes the whole thing, and you get a string back, which is like a Candid file printed. So there is another function in the Candid package, one of the latest versions. It allows you to take two interfaces and check if one interface is a subtype of another interface, which in like normal engineering language means this interface is compatible with another interface. So what I do in my code is just I write a piece of code which takes the string produced by the Candid macros, I save it into a file, and then I run the check to check like, the file I have on disk agrees with what was generated from my code. I don't have an example on slides, but if you want to see how to do it, I can put like a message on a forum later on, because I just more code that I can fit into a slide. So another point. So let's now talk about async programming a bit. The first advice about async is just do not combine panics with async. There is a deficiency in Rust implementation of async support right now, and like just let me start from the beginning. So the way Internet Computer Canisters handle traps and panics is a bit different from like normal programs. Because normal programs crash and start again. In Internet Computer, programs are rolled back to the previous safe point, which means and the safe point is like before you started to process the message or a callback. So if you initiate like async call, what happens is that the system suspends the execution, commits the state, and resumes it once it's receives the answer, like response. So if you panic after you receive the reply, you will be rolled back to the state before, after the async call was sent, but before it was replied, like before you received the reply. So from the Canister point of view, it will think that it sent a request, in our case, to store to like store a picture, I don't know, and it waits for reply. And because picture is like allocated in the future, it's still on your heap, but reply came and it broke the future. So the state was rolled back, and Canister still thinks that it is going to receive reply at some point, and still does not remove the memory, does not free it. So if you have like a big pile of data on your heap, which you only deallocate once you receive a reply, it will never go away, right? So you might have memory leaks. I mean, it's not a corruption. I mean, your Canister can safely process more requests usually, but until you upgrade, you can't reclaim the memory anymore. But yeah, it's one type of resource that you might leak with async. So like the next advice is very related to this issue, is that if you need to do some async operation, do not like lock any resources in your requests. So let me give an example. So assume we have a function which refreshes a profile, and it needs to go to a different canister to refresh. So what we could do is we use our lazy static model, for example, with logs. We get a log to get modifiable users. Then we find the user we want to modify. Then we issue a call to get the profile from a different canister, wait for this call to arrive. Then we like put the refreshed profile into the data and release the log. So the main problem is that the execution suspends before you receive your data, and the data, like the log, it stays like locked. So between so until you get your reply from different canister, all the attempts to grab this log again will trap. So for example, if you have another call which adds new users, or like reads even users. So so assume we started refreshing profile, we grab the log, send the request, commit to the state. At this point, user is still logged, and until we get the reply, they will stay logged. Then you have another call to add a new user. It tries to get users, and it cannot. So all the calls which need to like look at the users, they will trap until you get a reply. So this will result in a bad user experience, like you will have memory traps. So yeah, and one way of avoiding this is, again, use thread local. This could save you in this specific situation, because you cannot easily issue like a async call from a thread local, just because the API is structured that way. If you you need to pass a closure to which reads like global variable. You cannot pass a sync function, so it saves you from this issue as well. And the worst thing happens if you grab the log, issue a call, and then you trap after that, because at this point users are locked forever. So if you have both issues on this slide and on the previous slide, things are pretty bad. So yeah, let's talk about infrastructure now. So because some canisters might be dealing with very sensitive data, for example, privacy related stuff, or tokens, or like money maybe, they might need to inspect the code to check that they can trust what's running on the net computer. And for now, the only way to check like what's running on a net computer is to get the module hash, like hash of the WASP module. So the problem is now if you have the source code and you have the module hash, how do you check that they correspond to each other? And like the only way to do it is actually build the canister from the source and like check the hash and compare them. And this required your builds to be reproducible. So I'm not like a big expert on reproducible builds. I know it's very hard to achieve, but like the main technologies are Docker or any Linux container technology really, or Nix, which is like a reproducible package manager, purely functional. So I think Docker containers are much easier to start with. So consider just trying to make your builds reproducible. Then I prefer to build things with public CI infrastructure because it makes it easier to download artifacts and just look at what steps CI took to build your WAS module. And then if you evolve your canister, also make it easier for people to find the correspondence between revisions of your like source code and like which module hash was produced, so that people can see, okay, I have this module hash. I look at the release table, release, for example, releases in GitHub. I know, okay, this is release that was used to build this module with this hash. I can check out this release and try to build it on my own machine. Just some, like if you use GitHub releases, just consider adding your module hash to the release description. So upgrades, very complicated topic to talk about. So as you might know, on the internet computer, the way you migrate state from one version of your code to another version of the code is through upgrade process. So what happens is execution takes the old canister, it executes pre-upgrade method, which usually writes to stable memory. Then it instantiates like the new version of your code and calls post-upgrade method, which usually reads from the stable memory. And the main memory is just like dropped. So this means if you like ship a canister which does not support upgrades, there's no way you can migrate the state. So if your state was of any importance to you, it's lost forever. So before you like ship your first version of the canister to production, you need to think about upgrades. The second point I'd like to discuss is that you might want, I mean, you definitely need to use stable memory if you want to transfer any data between versions of the canister. So consider just putting a version number into stable memory somewhere so that you know how to interpret it, because stable memory stays with you like through all the life cycle of your canister. So unless you reinstall it from scratch. So just you can see stable memory as a like message to your future self, and then it becomes kind of a protocol, and then it's always a good idea to put version number in the protocol. So then if you do upgrades, please test them. I mean, the very first issue we had was untested upgrade hook, and it took a lot of people to like solve this issue. I will give like small advice on how to do it in the next slide. And the last piece of advice is a bit hard to follow, but I think it's a good one. Just consider using your stable memory as a main storage. It's very hard to do at the moment because basically you have like flat array. How do I organize my data in this flat array? Sometimes, like in the case of internet identity, for example, it's actually not that hard to do. And then all your upgrades are very smooth because they need to do very few operations. They just pre-upgrade hook usually doesn't even do anything, and post-upgrade hook just initializes some like metadata. And because all the data is already in stable memory, you don't need to do much encoding, decoding. So how to test upgrade hooks? So one approach that worked pretty well in practice is to use self-upgrades, as we call it, basically upgrade version of the canister to itself. And when you do it, like all the time, basically during the tests, I use Rust syntax in the code, but you can do the same thing in shell scripts or whatever. We just have our own testing infrastructure written in Rust. So the idea is that typically tests, they have some setup, then they do some action, and then they verify that the state is in this state of the system is like expected one. So what you do is you conditionally do upgrade right before the last step. So, and then you run all your tests twice. First with upgrades enabled, second with upgrades disabled. So imagine this piece of code is run twice with should upgrade equal to true first, and then should upgrade equal to false, like second time. So what this gives you is that now you can be sure that if you have an upgrade in the middle, the data like you set up front was not lost. For example, if you added something like users, I don't know, and then you made an upgrade in the middle, even though it's like upgrade to the same version of the canister, it's still important to like, even if you do that, it's like very good. It boosts your confidence a lot, at least in my case. I mean, I feel much safer if I do it this way. And yeah, we have quite a few canisters which test upgrades this way, and we found plenty of bugs using this method. So the last thing I wanted to talk about is observability. So as you know, it might be a bit hard to understand what's like the state of your program running on the computer. And in Dfinity, we use monitoring a lot. We collect tons of data about replica, about like canisters we're running, and so on. So in canisters, they're just software. I mean, you can use the same approach to monitoring, and like two main approaches we use to this. Yeah, so we use metrics, just collect data about canisters in the canisters themselves, and like fetch this data from time to time to figure out like what they're doing, what's like how many users you have, like how much memory you have, and so on. And there are two ways to like expose those metrics. One is just have a data structure with like metric as a field in a data structure, and you can have a query. If you don't want to advertise this data to like the whole internet, you can check that like the color of this method is the one you expect. For example, you can sign queries on your private data structure and fetch metrics in there. But you don't have to, of course. And the benefit of this approach is that you get data in a very structured form, like candidate, for example. And we use this approach a lot in our tests. So when we run some canisters on our testing infrastructure, then we just query metrics through the endpoint, and then we have everything parsed, and we can just access like data as we like. You can have for example, histograms encoded in a nice way, or like basically anything you can do with data structures is available to you. And the second option, which we use a lot in production, is just to use, if you have a monitoring system, in our case, we use Prometheus, we just dump data in the format which this monitoring system expects, and just slurp it from like Prometheus service directly and query it. And Prometheus, like the main format for Prometheus, just text-based format when you have like metric name, optionally some metadata, and then just metric value, and optionally some timestamps. So just simplest way is to use HTTP query gateway interface, and you don't even need a library. I mean, the format is so simple, you can just print the data. If you have histograms, it's a bit more complicated, but yeah, this works very well in practice because all the parsing is going on the Prometheus server, and it knows how to do it. So all our monitoring for canisters is built on top of this idea. Yeah, and I think that's all I have. I have plenty of examples of things done right and done wrong. So you might want to check out those canisters and examples in the Rust CDK. And I mean, they're far from being perfect. They made plenty of mistakes, but this is why I'm giving this talk, is because I don't want to repeat those mistakes. Yeah, and that's all I have for today. Thanks for your attention, and I would be happy to answer your questions.
Hello, Roman. Thank you so much for that. We had a very lively chat going on, and I can send you the chat transcript after. So I know that there's Hamish and others on the chat who are able to field some of the questions, but because we will be redistributing this on YouTube, I will re-ask some of the questions, even though some of them might have been answered by Hamish. And again, if anybody on this call has any questions, definitely feel free to drop it in the Q&A so we can field it to Roman. So Roman, first question here. How do you feel about atomic and RW lock?
I'm not sure I understand the question. I use them all the time in my code, but yeah, I mean.
Okay. If the original commenter wants to add additional color to the question, feel free to do so via the chat. So next question. Isn't thread underscore local exclamation point just a local thread, i.e. if I have a global state, it won't necessarily be seen across canister calls? Or is there some state safe magic where thread underscore local references will get transferred across calls?
Yeah, so there are no threads on an internet computer. Every canister runs in a single thread, and I don't think it's going to change anytime soon. So of course, it's thread local, but as long as you have only one thread, it works very well and saves you a lot of trouble.
Okay, great. Thank you. Next question. Would you recommend using the get underscore service macro?
I guess it's from Candid, like tooling. I mean, I think I use it exactly to check the interfaces. So I have my handwritten file, and I use this macro to get like automatically generated file, and then I check that they match. So I use this macro. I find this very helpful, but I still have like handwritten Candid file so that I can compare what is generated with what I wrote by hand.
Okay, thank you, Roman. So next question, how do I spawn a future with ICCDK, the equivalent of ignore in Motoko?
I see. I think there was a question on forum once. ICCDK provides a function which has a very bad name called block on. If you pass a future to this block on function, it will like delay it, basically will poll it until it's complete. You can think like in the background. So use this one. In internal version of the Rust CDK, it's called spawn, I think, which is the best name for it, most appropriate one. And there are actually two PRs to ICCDK, mine and Hans's, I think, which rename this function from block on to spawn. So short answer, use block on from ICCDK.
Okay, thank you. So next question. So Roman, imagine two functions in the same canister, both asynchronous. What happens if you call one from the other and await it?
It's perfectly fine. I mean, we do it all. I mean, it's the way it's supposed to work, right? You can call any await function from async function from other async function. So what actually happens, like if you enter a method and execution goes as deep into async functions as possible until the first await. So everything until the first await is executed, then, I mean, no matter how deep. And then it's not true. The first await, which makes a call. So because you have two types of futures, right? You have futures which return directly by ICCDK when you call something. And this is like a real async work. And you can have a sync function which does not actually block. So if you have a sync function which just returns 5, if you await it, it will return immediately. So here you won't suspend. So what actually happens then is when you enter the method, the execution runs all the way down until it hits the first call future. And when you await it, it will suspend the execution and will only resume it once you receive the result of the call. Yeah.
Great. Cool. Thank you. Thank you, Roman. So next question, why would two functions which are in the same canister need to be async if one needs to call the other? Wouldn't they get away with being synchronous and hence atomic?
Okay, I see the so one of the reasons you might want to do it is you want to, for example, split long computation into steps. For example, you know that you have 10K pieces of data, like 10,000 items, and you know that if you try to process them all at once, you just run out of cycles, because like execution has limited number of work a canister is allowed to do. So if you try to process everything at once, you just run out of cycles. So what you could do, you can kind of schedule calls to yourself. Like I process 1K items in one call, wait for result. It was just like second K functions, the K items in a second call, and like this way, the boundaries are different. Boundaries are like you make less work in each call, so and so you're not bounded by the execution time of a single call. Another reason you might want to do it if you want to do some piece of work asynchronously. For example, you want to do some ledger, for example, take ledger. Ledger creates a new block on the internal blockchain, and then it might need to like move some blocks to permanent storage to free up some space. So in this case, like the move blocks to permanent storage might be a sync function, and the client does not need to wait for it to complete. So you could just block on or spawn, depending on which CDK you use. Pass the garbage collection function to this block on. So basically execute this function asynchronously later, and then you just return a result. Yeah, so basically main answer is delay work until later. But generally, I would recommend to stick to synchronous code for as long as possible. If it works, just keep it synchronous. I mean, I wrote async support, and I'm not a big fan of it because it's very complicated for people to reason about. So as long as you can keep things sync, just write the simplest code you can.
Okay, thank you, Roman. So we got a clarification from Hamish around the last question. So he said, I think that last question was more along the lines of, if a canister calls a method on itself, does it execute synchronously immediately, or is it queued into the next round of execution?
Well, it's implementation detail of execution. So it's not like executed immediately on the same stack. I mean, we still have like this like suspend, commit state, resume. But it might happen that execution decides to execute this work immediately. It depends on the scheduling. I mean, we have a nice implementation in execution that if you like processed all the input to all the canisters, you still have some spare cycles left, and executing those inputs, they produce more work. You can like continue spending those cycles until you run out of them or run out of work. So it might happen that like routing happens in the same round. It might happen that you might wait to the next round or until you have your time slice. So it's hard to predict. But yeah, I would not recommend to rely on this work being executed in the same round. You might be beaten by it.
Okay, thank you, Roman. So we have two more questions. If you are attending this talk and you have more questions for Roman and you want him to get to it, please remember to drop it in Q&A. So penultimate question, if a canister call awaits one of its own public methods, Will that run synchronous and atomic, or will it break the atomicity as it does with the cross-canister calls?
Calls to self are not different in any way from any other calls, so it will break atomicity.
Okay, short and sweet. And then the final question, unless somebody has more questions, if I query an external canister and the canister query is rejected, how do I properly handle the rejection response so I can revert changes I made to the state before returning a response if the query happens within a canister?
Okay, so just to check if I understand correctly, you have a canister, you are probably in the update context, and you make a query to another canister and it rejects. And you did some work already before you made a call and you want to roll it back. And the decision to roll back or not depends on what was the answer, basically. So this is another excellent question. There is a feature which was requested on the forum, I think, and we also wanted to have it ourselves, and we have like a few design proposals to allow canisters dynamically decide whether they want to commit the state or not. So, so for now, you can either roll back the state and produce a reject, or you can produce a reply and then commit the state. This is sounds like a false dichotomy. I mean, you should be able to produce a reply and roll back the state if you want to. So we have exactly this feature in flight, and shouldn't be too hard to implement. Famous last words. I would also like to use it myself. So I hope we'll see it sometime in the future. But yeah, actually, when I think more of it, if you make a call, then your state is committed anyway. So you cannot use this feature. Even this feature won't help you in this situation. So I think it's even more complicated. So yeah, there are two approaches to this problem, maybe even more. So first is you can use fancy data structures. Just organize your code. I mean, simple answer, you just need to organize your code to make this workflow work as you want. So first approach would be you can use something like functional data structures. For example, if you have some map and you want to make a call and decide whether you add something to the map or not, depending on the query, or maybe you have like 5 maps and you want to update them automatically. So you can use what is called purely functional data structures, which work in a way that when you insert, they don't modify the structure in place. They create a new version of the data structure with modifications in place. And why it's fast is that because it shares most of the data with the previous structure. So you don't need to copy everything. You just copy the minimal amount which is required to add the changes. And there are quite a few implementations of this in Rust already. So one approach would be just you make a snapshot of all the data structures. You remember which version of so this is my users version 5, users version 6, or messages, I don't know, version 7. And then you make a call. And then in the end, if all the versions match, you insert the data into data structures and just swap the pointers to new versions. But there is obvious question what happens if version do not match, and then it's hard to decide. You might need to drop the changes and repeat the transaction. This will be like optimistic lock idea. And another thing which you could do is you could lock your data structures for duration of the call, but not lock everything, but just one little piece that you need to update. I think governance does something like that. It blocks blocks modifications to neurons while some iterations are in flight, and rejects all the calls which tries to modify the neuron while it's in this locked state. this will be like another way to approach this, like pessimistic lock approach. Another approach is just carefully organize the code and make it transactional. You can just remember what needs to be done when you collect all the data, and then, for example, remember I make a call. I want to add a user, but I also need a profile of the user from a different canister. So you just remember like all the updates you need to make to your state, but do not modify it directly. So you fetch profile. Okay, now you know I also need to update profile. You can accumulate it like a list of functions you need to apply, for example, to your state. So you continue accumulating pieces of work, and then you run them like, okay, now you don't need any calls anymore. You apply all those functions and commit the state, or reject if like some invariants were invalidated while all the calls were executed. And there was a reject, just drop all the functions you accumulated and nothing is changed in your data structure. So basically, I don't have a simple answer. We have the same problem ourselves, how to organize the code across calls. So this abstraction of like roll back the execution if something goes wrong is fine until you make the first call. And if you need to span multiple calls, then you need to use like traditional software engineering practices. And I mean, I described 3 approaches, but there are of course more. Sorry for a long answer.
Love it, Roman. So that was the last question. If anybody has any burning last questions, ask now, forever hold your peace. But otherwise, Roman, thank you so much for such a thorough and comprehensive talk on best practices for canisters written in Rust. Thank you to everyone in the audience for such a super lively discussion. And for those of us from Dfinity who are also on the call to help answer questions in the chat. And hope to see you all at the next community conversation. Bye, everyone. Take care.